To make sure everyone's in the right session, this is DAT329, Data Modeling Core Concepts for Amazon DynamoDB. My name is Greg Crum. I'm a senior DynamoDB specialist SA with AWS. So talk to customers all day long about DynamoDB, quite enjoy it. I'll be joined here shortly by my co-presenter, Akshat Vig. He's a senior principal engineer on the DynamoDB service team. So what if I told you that your database can scale seamlessly by default? Or that it could support future use cases without a complete redesign? And how about that complex relationships can in fact be modeled on DynamoDB? We're here today to talk about data modeling patterns and principles for DynamoDB and how to prepare your schema for scale. Today we'll talk about how we do data modeling at AWS. We'll go through some key DynamoDB concepts to make sure everyone's kind of on the same page. We'll talk about a fictional use case we have here, just to have a consistent pattern for the schema we're talking about. Talk about table design choices, multi-table, single table. I'm sure some of you have heard of that. And then talk about some schema building blocks. That's kind of the bulk of the session is, what patterns can we bring in to make the right schema for scale? And then in the end, we'll kind of recap what we talked about, make sure you're ready to go work on your schema yourself. So some key concepts. In DynamoDB, we don't deal with clusters. There's no servers, instances. We don't have versions. You don't have to do maintenance windows. It's really great. The highest level of abstraction you have to care about is just a table. Nice big box to put stuff in. In that box, we put items. And items can have an arbitrary selection of attributes with them, but they still have to have two particular, very important parts of them, which we'll talk about here, the keys. So we choose a partition key. This is how DynamoDB figures out where in the massive multi-tenant scaled system behind the scenes to put your data. And then you have an optional sort key you can put on the table to start sorting data within that particular partition. So we can start selectively finding parts of that data within a range with certain prefixes. We'll get into schema design choices for sort key shortly. One thing I always like to point out here is all those other attributes can be whatever they want. We don't enforce a schema except for the keys on the table. So we can have different kinds of items within the same table, which gives us a lot of power to choose specifically what data we actually need to store. We don't put nulls, we don't have to put empties, just put only the attributes you need. So the partition key and sort key together make up the primary key. That is a total, you need to make sure that is a unique pair of attributes. If you create a table with just a partition key, you're treating us as a key value database. The partition key is the primary key, and then any other attributes are non-key. So those other attributes come into play. Another key idea about DynamoDB that we want to make sure everyone's aware of, we have indexes. There's two kinds. There's local secondary index, which we're not going to have an example of today, but there's also global secondary index. Think of this as a second table that we run on your behalf. We replicate data to that table. We make sure that it abides by the partition and sort keys that you chose for that index. So in this example, you can see the first GSI, we've flipped the attributes. So what was the sort key is now the partition key, and what was the partition key is now the sort key. It's a great way of doing many-to-many relationships in DynamoDB. Just immediately, we have a reverse lookup on our table. GSIs also don't enforce that it has to be a key from the base table either. You could see we've brought in A5 or A4 for the other GSI options. But to guarantee uniqueness of each record, we still bring over the partition key and sort key from the table. So you see A1 and A2 will always be in the index. We can selectively project certain attributes, so we can use an include statement at creation, or we can just project all, which is the bottom one. Every attribute comes over. So for GSIs, we have a lot of power to start kind of flipping the perspective of our data around. Usually databases have multiple personalities that like to look at the data. Your company wants to look at it a certain way. Maybe your customers want to look at it another way. So that kind of brings us to our use case here. We're going to talk about a project that you all have been tasked with to build a new e-commerce platform. Exciting. And to build an informed data model, we need some key attributes about our project. We want to know what entities need to be stored. Even though we're a non-SQL or a NoSQL database, we still need to think about an ERD. It doesn't matter how we connect them together necessarily. We'll get to that shortly. But we want to know what they are. We want to know how they're accessed. You'll hear a lot about access patterns when you look at DynamoDB, because for our database, we need to store the data as we intend to read it. We don't want to do joins. We don't want to start computing anything on the client. We want to make sure everything's pre-computed, pre-stored as we intend to read it. And finally, an approximate size of each entity, whether it's high cardinality or not, and the approximate throughput. Those can kind of help us choose different patterns we can put in place. We'll get into some building blocks of how to handle different throughput and cardinality later. Example ERD we have customers. The goal of an e-commerce platform is to get a customer and connect them to a product. And we usually do that by letting them add a product to a shopping cart and by placing an order, hopefully, for what's in their shopping cart. Now for the access patterns, we have a few examples here that we're going to talk through. A customer wants to add the product to their shopping cart. Customer maybe wants to save it in the cart for later. We don't want to buy it right now, but I want to keep an eye on it. Maybe create an order for only the active items in that cart. So ignore saved, but I want to buy what's actively in my cart. After I've purchased something, I want to go see what my most recent order status is. Maybe look at the products on that as well. Maybe some of them have shipped, some haven't. I want to figure that out. Now you and your company have a different perspective. You want to view what orders are unfulfilled. The customer obviously wants to know that, but you need to figure out what to ship. And then also you need to update an order to mark it as shipped. So two completely different personas accessing this data. Think about the perspective of who's making that query. What persona owns the access pattern? Now finally, a couple key attributes about the entities we've talked about. Kind of list out the entities. We want to think about the cardinality. And cardinality is just how many unique items in our set there are. If we have an e-commerce store that sells one product and one product only, that's a pretty low cardinality. If we have millions of products, that's higher cardinality. Because odds are good, multiple people will be looking at completely different parts of the data set. Customers is pretty high. Customers and shopping carts and orders are pretty tied at the hip. And also, it's good to keep in mind the average size of those entities. In DynamoDB, we have a billing model that is by bytes written. And so it's not necessarily about CPU or memory anymore. We want to think about optimizing the item size. And we have a maximum item size of 400 kilobytes. We also want to think about whether we're approaching that for a given entity. We're not a blob store. You can try and use us as that, but S3 is better. So one of the first questions you should ask yourself, and this applies for any data modeling, how should I organize the data to meet the specific needs of the application? This is particularly important for NoSQL because, again, storing it as is intended to be read is very important for optimizing. Now, I like to think of this kind of like building a house. To build a good schema, you need to start with a solid foundation. And this kind of boils down to one of the questions I am asked the most in my day-to-day job. How many tables do you need to store the data? And Some people are Puritans and say one table per entity, or even one single table for all entities. But that's not a hard and fast rule. There's usually some flexibility that needs to be allowed here. You're probably going to end up with a design that has multiple tables, but also some entities are stored in the same table. So some questions to ask yourself. Do I have any workloads that have a specific priority? Maybe there's a table that has new orders coming in. I want those to be treated differently than archived orders. Obviously, maybe for compliance, I need to look at orders from 2 years ago. But that's not really a priority. It's some business analyst running a query. Are multiple entities accessed together? I like to think of this from the perspective of the UI I'm building. If I'm on a web page and I see this entity and this entity always return together, maybe I should put those together on the database, either in the same item or multiple items under the same partition. Access control. If we want a customer to own a part of the record set, but maybe there's some compliance reason that we don't want them to access this other part, maybe those should be in separate tables. We can put a different IAM policy on the table and then filter down who can access what a little more granularly because they're in separate tables. And then also, do we have any downstream services that rely on the data? Once we put multiple entities into the same table, they're going to show up in the same stream of change data capture. They may show up in the same backups. Do we want those together permanently? Maybe not. So one of the first examples then is, what if we choose multi-table design? It's a little more like traditional relational databases. I have one entity in one table, one entity in the other. It's easiest to implement for most people who are new to NoSQL because it's just what you've been taught. Now, data within each table will be accessed independently, but what happens is if you need both at the same time, now you're essentially computing a join on your client. Maybe you had to retrieve too much data from table A and too much data from table B. Finding the overlap kind of wasted resources. Because we can't join between these tables for DynamoDB, this doesn't always end up being the best solution, but we have some benefits. These entities don't need to abide by the same structure. Maybe we have a different key pattern. Maybe one entity only needs a partition key, but no sort key. There's ways around that, which we'll show shortly, but allowing the flexibility for each table to choose its own structure can be good. For indexes and streams, we're going to keep those extra items out of there if we don't need them. Each table can also have its own storage class. We now have infrequent access storage class, so perhaps that archived orders table with 2-year-old orders can be run with infrequent access. But if we kept that data in the standard primary table, well, now we don't get the discount of running it in infrequent access because it has to abide by the table class that everyone else is. We can choose different backups, different retention policies. We get that fine-tuning that we can bring in by keeping them in separate tables. And then also, one of the big ones, reduced learning curve. Not having to learn single table design tends to be one of the reasons a lot of people choose multi-table, because its time to market is always a valuable resource to hold on to. The alternative is more like this, single table design. We have a partition key that is sort of the entity that everything is related back to, in this example, a user. And then we have a sort key that is overloaded with different prefixes to have a hierarchy built into that partition. We can have different entity types based on the prefix that we give them. In this example, we have address information, shopping cart information, sort of pulling back the curtain from slides of future, but we'll get there. Some of the benefits of single table design end up being that you have data locality. If you run a query for 3 entities all with that same prefix, you can get them in the same query. One of the benefits of DynamoDB's query and scan APIs are we will merge together the total size of items when you read them. And we bill in 4 kilobyte increments, so if you had 4 1 kilobyte items in one query, even if they're different entities, you're billed as if you read just one, because that turns out to be 1 RCU strongly consistent or half an RCU eventually consistent. Another benefit is throughput will be shared across all entities in this common table. So if you have, say, orders with a pretty low write or read rate, but then you have products with a higher read rate or customers with a higher write rate, we've smoothed out the curve. The spikiness of traffic is now shared across all of them, and we don't have to worry about the capacity being over-provisioned as much because they've all kind of evened each other out. And as I said, query optimization, when we generate these multiple, or when we return multiple items in the same query, then we can share the RCU amongst them. So right now, let's make the assumption we're going to start with a table per entity. So we've got a customers table, products, carts, orders. Let's just start there. It's usually a good place to start. We don't want to just immediately assume multi-table until we know a little more about what our schema design is going to look like. All right, so now the meat of the talk. We talked about building the right foundation for our data model. We need blocks. We need things to choose to build the right structure. Do we want brick? Do we want, something else? So we're going to build those blocks on top of that foundation. Now, one of the most important things when choosing a schema for DynamoDB is you need to pick the right partition key. And to give you an insight into why that matters is, let's say we have an item come in. Our partition key in this example is order ID. Just give it a 1. Now, behind the scenes, DynamoDB is running multiple partitions for your data, and we're going to divide each of those partitions across a key space. So a lot of zeros to a lot of Fs. The reason that matters is the partition key used to be called the hash key. We are passing its value into a hashing function, and the output of that hashing function is a hash, zeros to Fs. And now the output of that can be mapped to a specific partition, which is a certain server or storage node in our case, of where the data for that partition key is supposed to live. So we've outputted the hash for this is 7B. Well, we're going to put that over in partition B. This is a repeatable hash function. So anytime we want to write data with that same partition key, anytime we want to read data with that same partition key, we know exactly where to look. You could end up with thousands or tens of thousands of partitions running your Dynamo table, and to point to all of them to get one item is not efficient. We are sharded by default. You have to know where in the partition space that data lives. So choosing the right partition key, the higher cardinality, the better. We want to think of it from who owns or what persona is accessing that particular entity. Most schemas, even in the relational world, if you kind of draw out an ERD, there's probably one table at the core of it all that everything just bumps off of. Let's start there. And then we want to make sure the key is used for most patterns. Let's not pick a partition key that has 2 of the 50 access patterns. Let's start from the most common access pattern and go. So for e-commerce, we're thinking of customers. Now look, it's going to be a little hard to see you all, but quick show of hands, who thinks a customer's last name would be a good partition key? Anyone? No. It's not very high cardinality. We're going to have a lot of repeats. More common names are going to be, you're going to end up with maybe a hot partition on the name Smith, but not as hot of a partition on others. So we're kind of imbalancing it. How about email? Anyone? No? Email's better. The one problem with email is, what if someone changes their email? Now we have to go change every item that has the customer's email. So I guess lastly, how about A random ID, like a UID, GUID. Anyone? No takers? All right. Yes. The UIDs, GUIDs, those are my favorite partition key because let's be honest, it's a computer reading this. I don't need sequential numbers. I don't need a key that I can go have the customer look at themselves. This is abstracted away from the customer. We want to make an ID that is as random and high cardinality as possible, and you can't really get better than randomly generated IDs. Now, how about the shopping carts? What about a UUID for the shopping cart? Just its own cart ID. Anyone? No? Okay. This one's a bit of a trick because, again, let's go back a few slides. Who is the persona that cares about that shopping cart? It is not the cart itself. It's the customer. So in DynamoDB, we want to think of buckets of data. The partition key is a way to bucket data. And the customer cares about their bucket of data. They don't care about other customers' data. So what we kind of end up with here is the partition keys for almost every entity we're talking about are customer ID. Products, they're their own thing. We want to manage them independently. A customer does not own a product. Now, what about one-to-many relationships? These partition keys only get us a key value lookup. That's where sort keys need to come in. Sort keys will group related items under the same partition key. Again, I kind of gave you the sneak peek on the single table design slide, but we're going to make a sort key that can return multiple items at the same time, potentially. And then also, the sort key can be used to improve query performance because we don't have to read the entire partition. We can read only a range within that. The sort key used to be called a range key. So one common example is a sort key of a date time, like an epoch timestamp or ISO 8601, which is year, month, day. And you can then say, I want my sort key to be between a week ago and today. I've now found the last week of orders, and I've ignored everything else. So the power of the sort key is quite useful for fine-tuning those queries. And then access can be split across multiple small items instead of one large document. If we maintained a single customer record, and every order went into that customer record, and every payment history and everything, we would just have an ever-expanding size of item. And we do not want to design for unbounded growth. We want to design for tactically small updates, reads, inserts. The smaller we can keep those reads and inserts, usually the better. Akshat will get into that in a bit. Now, once we bring the sort key in place, so here's where this starts looking. Still have our partition space. We have a customer with places a new order, and they come in and make another order, and we can know that that item will be placed right next to the other order. We can retrieve both at the same time if the customer asks for everything, or we can ask for one specific order by saying sort key equals order ID. Now this ends up looking a bit like this in a table. Notice that the customer has multiple orders under their partition for customer 1, 2, 3. 4, 5, 6 is a completely separate bucket. They're not even aware of 1, 2, 3's orders. Again, we kind of need to think in a slightly multi-tenant way here, as you're going to have internal tenants, like customers, potentially, and you need to keep their data separate in most situations. We may make an index that combines them later for our use, but from the primary use case, let's stick to the customer persona. Now, that kind of gave us a quick one-to-many. What if we want to build a hierarchy into our data model? You know, most entities have multiple types or statuses. I alluded to the shopping cart having saved and active earlier. So this is where we start building composite sort keys. So we still have our customer partition key, but now we're going to build a prefix structure in the sort key. So one of our most common patterns is to use a hashtag. So we'd start with the entity type in this example. It's a cart. We hashtag status. So active or saved, we now have the ability to figure out whether I want to look at everything in the cart or active only. And then we're putting the actual ID of what we're pointing at. So this is the product SKU. And then the flexibility here comes where with this prefix structure, you see at the bottom we have wish. Well, maybe marketing came along and told you, we want to have a wish list feature now. Well, we've already started bucketing cart items into the customer partition. Let's just add a prefix of wish, and there's the flexibility. We've added a whole new feature without adding a table. We haven't changed our data model. We just put a new prefix type in place, and we can selectively query it if we want. So we could say partition key is 123. Sort key begins with cart #active. The sort key, think of it as a lexicographically sorted left to right, almost like a dictionary. It's a lot easier to find something in the dictionary if you know the letter it starts with. And so the sort key, we know the start, and we're going to ask for anything that begins with cart active. So that will return apples and bananas. We could also say cart saved. That returns the other two items. And then I don't have it in the slide, but we could say begins with cart, and we get all 4 items back simultaneously. Think of it from that UI again. What am I looking at? At least Amazon shopping cart page, they show you a list of active, and then they show you a list of saved, but it's all on the same page. So what we kind of end up with at this point, going through schema, is we've had some sort keys for cart. We're going to do order items. If we do single table design and we want to keep these items together, let's assume customers and products don't need an extra identifier for their sort key. There's really it's a product ID, it's a customer. There's only one record for each of those. We could just give it a generic SK, like exclamation. Think of it like DNS. There's a root record with an @ it's the one root record. So for right now, we're going to have that as our sort key. All right, and now I will turn it over to my co-presenter, Akshat, to finish the rest of the talk. Thank you all.
Perfect. So engineering is not just about adding features. It's also about building cost-effective solutions, right? So in next set of slides, I'll talk through some of the strategies that you can use to optimize the cost of using DynamoDB. So let's start with item sizes and write capacity units. If you look at an item in DynamoDB, if you're doing an update, for example, or a write for that item, if the item is 100 bytes, it's going to consume 1 write capacity unit for you. Up to 1024, it would be 1 write capacity unit. And you can just keep on incrementing it based on that. You can have as big items as 400 kilobyte, and that will consume 400 WCUs. And as Greg pointed out, there are always trade-offs with using larger items. If you have bigger items than this, yes, you probably need an object store. You can build an index in DynamoDB, store data in S3. But with 400 KB item, things to keep in mind is that it's going to, since the items are large, it's going to increase your read and write capacity units, right? You're consuming almost 400 WCUs for write and 400 RCUs for a read. It will be also higher on latency for reads and writes because you're just moving a lot more data in the single call, and potentials of encountering throttling. So DynamoDB, we partition your data. If you're storing 400 KB items, and they all are grouped on the same partition, and if you do 3 writes on that partition, since the maximum right now on a partition is about 1,000 WCUs, you will start getting throttled if you do more than 3 writes concurrently at the same time. So it's not that you shouldn't completely use this, but these are things to keep in mind while designing your schema that, hey, if my item size is 400 KB, then potentially I'll run into these issues. And why is that? So as Greg pointed out initially that if you have, what happens behind the scenes when you store an item in DynamoDB is the item is hashed based on whatever your partition key is. It's sent to the storage node, and on that storage node, it will be written. And how that happens is, first thing that storage node does, it looks up the item from the engine. So these items, if you already are storing something there, we will look that up and identify, okay, what has changed in this item, apply that change first in memory to make sure everything is good, all the asserts are validated, and then finally write it back to the engine. And now, if you have a 400 KB item, it's basically we're going to read the full 400 KB, and if you even update like a small part of that item, you're going to pay the full cost of 400 KB. And let's take an example for it. Let's say that you have orders stored as a big giant order document, and it keeps on growing, and maybe it's like, for this example, let's say it's like about 20 KB, right? And within this order, you have order lines, like you're selling apples, oranges, or what have you. Now, as you are changing the status of the items that are getting shipped, let's say each line item gets shipped, and you want to change the status of that particular line item, saying that, hey, apples shipped, let me go and update the status, right? So your status update, like what is the size of it? Probably 20 bytes, right? But based on what I explained, since the item size is 20 kilobyte, you will end up paying 20 WCUs for your write operation, right? So what you really want is just those 100 bytes or whatever 20 bytes that are going to get updated. So what do we do? Like, how do we optimize the cost for this specific use case where I do have an order document. I want to store it together because of all the goodness that it brings with it, but I want to optimize my cost. So the trick is break that item into smaller items, and next question is, how do you find out like what those items should look like, right? Few nuggets, like you can just think of it like logical breaks. For example, order lines is a logical unit for the order, so you can store all of them as separate items. And you have like static versus dynamic content in the order document. For example, customer information. That's not going to change that often, so you can store that in the big rest of the part of your document and have things which are going to be frequently updated stored as separate items, right? So that's the access frequency. You want to update the order status throughout the life cycle of the e-commerce application. And then the last one, data integrity. Like you want to ensure that all the customer details and order details, whatever you're storing, you store them as like related entities, and so that you can pull them together if you are looking for like a consistent view of your data. Because if you have multiple items, you do a query, and you might have to paginate those, right? So in this example, and this concept is called as vertical partitioning. So in this example, the big order document that I had, I've split it up into separate order lines. Apples is one, oranges is one, and I'm storing quantity as well. And then there is status, which is pending shipment right now. What does it help? Now, if you want to update the item, like update the status of a specific item, you can just say, this is the primary key, customer ID. This is the order line key, which is the sort key in this example, and you can set the status for that particular item. Now, how much you're paying for this? Whatever is, if you're changing 20 bytes, it's going to be just like 1 WCU, right? So instead of the full load and write back of 20 WCUs, you can really reduce your cost by 20 times. That's massive savings. Similarly, like you want to load the customer data, right? You want to show everything now. So you can do begins with on the sort key so that you get all the order line items. Let's say you want to show for this order what are all the order lines that are there on a single page. Take the customer ID as the hash key, the primary key, and then the sort key being the order specific order number. Pass that as the begins with part of your query, and you get the whole thing in front of the customer. So quick recap, benefits of vertical partitioning. Improved query performance, as we looked at, now you're doing like specific reads and writes for the items. If it is 1 KB, it is only going to be loaded 1 KB item, so your performance will be fast, super fast, because DynamoDB, it's designed for single-digit millisecond latencies on the client side, right? So you get improved query performance. You can reduce the cost of storing and updating the items in your DynamoDB table. You can model any type of like nested structures as like separate line items. As we saw, we broke the order document into smaller chunks, and there might be other similar nested structures that you want to store for different entities like customer address information, what have you. One more important thing that you gain out of it is fine-grained access control. Let's say you want to keep some information, even like you don't want to give access to some of the items to everyone. You can do fine-grained access control on that specific part of the table, right? So you can say that, hey, I do not want my address information to be shared with everyone, whoever are the different personas of the table. You can set IAM policies which restrict access to certain items to certain users. So fine-grained access control is another big advantage that you get out of it. And scale, like we are talking about designing schemas for scale. Build an application that gets millions of writes or hundreds of millions of writes per second. Since you have optimized your schema to write based on the access frequency of the items that you're going to update a lot more, your performance will be better on the client side, your customers will be happy, and you'll save cost. So everyone is gaining out of this. It's a win-win. So engineering is about trade-offs, right? What is the trade-off? Like, what is the thing behind it? Like, what do I lose by doing this? So if the 20 KB item that I had, 50 KB is what is shown here. So if you break your 50 KB item into 3 different items, one is 500 bytes, second is 500 bytes, and rest is 49 KB. So 2 order lines and then rest of the customer information and order information. When you do a write, instead of costing you 50 WCUs, now it's costing you, you can see 51 WCUs because you are doing 3 different writes. 500 bytes, we charge you 1 WCU. 500 bytes again, 1 WCU. So you might end up paying higher cost of setting up the items. But if anyways you know that I'm going to update the smaller part of the whole thing more often, it's going to save you 50 times every time you're doing that update. So even though this is a trade-off, it's pretty good. You're still getting pretty good savings out of it. You might pay up the cost upfront to set it up, but later on you're gaining those benefits of repeatable reads and repeatable writes that you're doing on part of your data model, which is frequently accessed. So your schema, order lines is essentially, we broke it out into a separate table, and you have customer ID as the primary key and sort key as the order lines. And it's not just this. There are more tips for reducing your cost, which I've linked few articles here. These are about like evaluating whether you have auto-scaling set on your table. Things like, even very simple things like if you have attribute that you're storing on your attributes that you're storing in your DynamoDB table, how do you name them? If you name them shorter, right, you'll end up paying lesser cost. So very simple tricks like attribute name compression. If you have like an attribute name which is 10 characters long versus 1 character long, you're saving 10 times on the storage cost, and every time you're doing a write. So very, very simple tips. I highly encourage you guys to take a photo of this and then read these. It is crafted techniques over years for helping you out, save cost. All right, so now let's talk about filtering data. Now databases, you store data in them, right? And data modeling is about, as I said, efficient schemas, and filtering helps you achieve that as well. Now what I mean by filtering is there are multiple ways you can filter data. You can do on the client side or you can do on the server side. Now on server side, there are 3 ways in DynamoDB that you can do it. You can filter using a partition key and a sort key, as Greg pointed out. Like that's why you have to choose the right partition key for your table. You have to choose the right sort key for your table so that your access pattern / API that you're building is mapped perfectly to that, and you are able to build your schema for the most highly access data, right? Second one is using secondary indexes, and this is about local secondary indexes and global secondary indexes. I'll take few examples in the section about the global secondary indexes and few techniques behind them. And then third is filter using a filter expression. We're not going to talk about filter using filter expression. Like, think of it just like you're doing a full scan on your table and then specifying some filter conditions. So in your orders table or order lines table, you want to find out all apples. The one way to do that would be just do a scan and then filter out apples as you're making those queries. So as I said, Greg already covered this section. We are going to zoom into filtering using keys on a secondary index. Now let's going back to the example that we have. How do you get list of orders, all the orders that need to be charged and shipped, right? If this is the question that you're trying to answer, and we had the order lines table which had customer information as the primary key, and then we had all the information about the orders in the sort key, and you want to find out like customers who are charged or not charged. As I said, you can do a scan with filter, but you'll end up paying a lot more cost. So think about if you had those 20 KB documents stored in DynamoDB and you're doing a scan of all those items for each call that you're doing, you're essentially paying, even though it's happening on the server side, you're paying those read RCUs that are being spent to give you the answer. So scan with filter, that's the last resort. Don't use it. Think of it as if you can build a global secondary index for the access pattern. And what is global secondary index? It's just like a DynamoDB table that we have built and managed for you. So in the sense that whenever you do a write on the base table, all those writes are replicated to the index as well. And you can have many indexes, many global secondary indexes on your table. There is one thing about indexes is that just like you choose the schema of your base table, you need to make sure the schema of your index is also high cardinality. Otherwise, you could run into the same hotkey issues. Like, for example, don't choose a cardinality of true and false, right? All the items will jam into that index from different parts of the base table, and you will end up causing throttling on the base table, which will be returned back to the client, which means they'll see an availability impact on your application. So now to get that information, what we just discussed, how do I find out customers who are not charged? In this example, let's say that customers who are not charged, we are storing the sort key as the payment date. And this is the date when the customer should be charged because the item will be shipped at that time, right? Let's say you have built your data model like that, and then you have like a process which is reading this table, finding out what all items I should pick up and start shipping and start charging customers, right? Now, in global secondary indexes, when you do create a global secondary index, you can do different types of projections. You can do just keys, which means only whatever data will be there in the index will be purely just keys that you add for the index. So in one of the examples that we had, if you just pick the customer ID and the payment date, only those two fields will be there. If you say, I want only keys in my global secondary index. If you say include and I want to pick up like specific attributes, that's what I did in my example where I picked up the customer ID, saw the payment date and few things. I skipped few things out of the overall item that I didn't want to have in my global secondary index. Or you can say, you know what, I'll just have the full data copied in the index, because I can then do all sort of things on that index as well. It's just like another DynamoDB table, right? Benefits of global secondary index. Again, you can think of it like you can improve your query performance by specifically picking the use cases or the API that you're building for your application, which your customers will call, and store that in the index so that you get, maybe you only project 3 attributes. So you are again going to reduce your cost of repeated access on a smaller subset of your table. You can reduce cost of storing and updating large items. You can do workload isolation, which is one of my favorites out of this, where in the sense that if you have like your base table where you are doing a lot of writes, and then you have another index that you created, and you have 2 different workloads. One workload is about, again, higher priority reads that I want to do on the base table, and then there is like this business analytics use case, which I will probably be doing like once in a while to read. So you can do read from that particular index. And obviously it gets you efficient data filtering, so you get like reduced cost of reading only specific parts of the item that you want to read. And then again, we are designing schemas for scale. So you can have your application as many indexes, like you can have 1 index per use case that you want, and you can, that's how scale your application, scale your data, and keep your customers happy. So going to the example of what the index that looks like. Let's say that in this particular example, you want to find out what all products were sold to what customers. So you have a product index, and then you have your sort key as apples, and then customer ID as your hash key as product, which is apples or oranges, and then customer is your sort key. So you can do apples as who all bought apples, who all bought oranges, and stuff like that. Now, as I said, just like picking up the right key for your base table, it's important to pick the right key for your index, because if you have a low cardinality index schema, all your writes on the base table will be sent to the index. And since index has limited capacity as well, just like resource constraints, if you have all the million writes going to a single item, it will become a hot item, and you will end up getting throttled. So make sure that your schema on the index also has high cardinality. Now again, trade-offs for global secondary indexes. Cost, you end up paying more cost because you're creating another, like storage cost, because you're creating another replica of your data. Like if you do project all, you essentially have the full table replicated as a new index in DynamoDB. Write contention, if you cannot design a schema on the index which is high cardinality, you'll run into write contention on your hotkeys, and corresponding to that, you will get throttled. Consistency, like global secondary indexes, they're eventually consistent. So you do a base table write, and it'll take some time for that write to actually get replicated to the index. And when you do a query on your index, whatever data you're getting is eventually consistent. And management, you have to create, maintain, update indexes, you have to monitor them, and things like that. Not the greatest worry, but yeah, again, for every choice I'm explaining the good sides and the potential things that you need to consider for trade-offs, right? Now, coming back to the question that we were trying to answer, how do I figure out what customers need to be charged and the orders need to be shipped? One way we discussed was you just scan and filter based on the payment date, right? But that would be expensive. So we can essentially create a global secondary index for this, where your hash key is the order ID and your sort key is the payment date. Now, what this creates for you is a sparse index. And like what I mean by a sparse index is you are essentially selectively picking items from your base table which should be projected based on if certain fields are there in your base table or not. So in the example that we're looking at of payment date, as I said, let's say your application writes the payment date at the time of like creating the order, but once the order is shipped and charged, you just remove the payment date from the order, which means what will happen is, let's say your base table, orders table look like this. You have the customer ID, order ID, payment date. If you look at the third one, the customer third, order ID 3, it is already shipped. The customer is charged, and you don't have the payment date on this particular attribute, right? The value for the payment date is not there. And what will happen on the index is that things which are actually present, which means the first two items, if you create an index on order ID and payment date, only those two will show up on your index. So that's your sparse index. And this really helps again to reduce your cost on the index storage, reduce your read cost that you're doing. Your application, as I said, is waking up, scanning your sparse index to find out which all customers I need to charge. You're essentially not wasting any RCUs to find out customers who are already been charged by your application. And now how your table gets updated. You do an update item and set the status as shipped and remove the payment date from your base table. Automatically your index will get updated and that particular line item will get removed. So you have charged the customer, order is shipped, and you're golden. Now, benefits of sparse secondary index, very similar to what we saw from what I explained for global secondary indexes, that query performance is improved because you are like specifically projecting things that your application cares about in your sparse index. You read smaller items because if you have 20 kilobyte document, you don't have to again project everything in your sparse index, and you reduce your cost as I explained, get workload isolation. You can have very high read throughput on your index, whatever your application needs, right? You can provision your index corresponding to that, and you get scalability. Again, designing schemas for scale, and these are things that I have also done. And I have also helped customers in multiple applications that they have built or I have built using DynamoDB. So overall, recap on key principles that we discussed today. Model your data in that is efficient for common queries and operations. I would say just think of it like an API. If you're designing an API, that's your access pattern, right? Like get order or update the cart. These are APIs that you're building. These are your access patterns. Think of them like that and make sure you model your database table like that. We looked at how many tables you should have. Should you do single table, multi-table? There's no one size fits all. It varies by data and query pattern. So I wouldn't say that, oh, you should only do single table or you should only do multi-tables. Most often I see customers having multiple tables, and maybe some tables are actually storing multiple entities. Like one example, we built DynamoDB transactions, which is a customer-facing feature. We actually store all the requests that you're sending in using a lot of concepts that I explained. Like we do vertical partitioning to store multiple parts of your transaction that you are going to do, things like that. Again, we are using that particular model. We're using some parts as multi-table, and some parts have the single table design of it. Design the data model based on access patterns for optimizing your utilization on your table, as we looked through multiple examples in the talk. Good partition keys, distribute data, and reduce hotspots. As Greg pointed out, if you use UUIDs, that's amazing. That gets you the best distribution, but might not be applicable for different personas, might not be applicable everywhere. So think about the personas, think about the APIs that you're doing, and then choose the right partition key. And then you can obviously add indexes as you go. Optimize cost. engineering is about cost efficiency as well, right? Like it's not just about adding features. We looked at multiple ways we can do optimization on the cost, vertical partitioning that we went through the example. I also talked about attribute compression, like if you're storing address, just store it as ADD instead of full string address as the name, right? There are other examples on the articles that I linked. For example, you can set TTL on your table, and all the deletes that happen on your table based on TTL will be free. Otherwise, you have to do a delete item, which will cost you, if you have a 20 KB item, it will cost you that much, right? But we can identify, if you set a TTL on your items, we can identify behind the scenes what is the most optimal way to get rid of those items and do it for you. And then using global secondary indexes, you can improve your query performance by specifically adding indexes for the use case that you are targeting, and also, again, improve your read cost that you're going to do. Your write cost will increase, obviously, because you have your base table, and then corresponding to that, you have an index which you're maintaining for your read pattern. Again, you have to do the maths on whether it makes sense or not. In some cases, maybe scan with filter is fine. With that, there are a few additional resources for data modeling, like there is NoSQL Workbench that you can use. You can download on your desktop and play with it. A lot of links on data modeling documentation, which are linked from this. And then there is a book by Alex Dibry, the DynamoDB book, which talks a lot about these concepts and in a lot more detail. I highly encourage you guys to look at that as well. With that, thanks a lot. It was a pleasure to be here to explain these concepts.